today we're going to deal with all kinds of functions. I'd like to call this kind of a review of kind of like it ties together everything we've been doing the whole semester. I really am happy, very pleased with being able to present this to you today. Okay. Alrighty. So, got functions. Who can tell me what type of function? Oh, perfect. Look what happened. I just died. Hold on. Okay, Michaela, do you have an answer for me? That's a step function. But the formal name of it would be a greatest integer function. And it's a greatest integer function because whatever's inside of those brackets right there, in order to simplify it, when it comes outside of the brackets, it has to be an integer. Okay, and we're going to go over that again because I know it's been a while. But I think that's kind of why they call it the greatest integer function. It's also called a step function. What about this one? Yeah, it's pretty easy, right? Absolute value function. And this one? Second did this too. It kind of surprised me. It's a quadratic, right? You guys have done those for quite some time, right? Quadratic function. So go ahead and just sketch those quickly on your notes and make sure you have the names of them. 2, 1. Okay. Can you name these functions? What'd you say? It is a linear function, yes. Specific. It's a specific type of linear function. It is a parent graph, absolutely. That's what I would call it. But this is like book specific. It's called an identity function. Right? When something's x, it's also y. When x is 1, y is 1. When x is 2, y is 2. That's why they call it an identity function. What about this one? Double identity. Identity times 2. Hint, we just did it. It's a direct function, right? Yes, it's exactly because it's in that form. It's a direct variation function because it has no b, right? Or because a direct function always goes through the origin because it doesn't have a b. So it's a specific identity function, specific type of linear function. Direct variation function, a specific type of linear function. Okay? What about that one? Which I'm not even going to make you guess on because we really never said it, but it's going to make sense when you see it. The constant function. Why would we call that a constant function? Okay, it's constantly -1, true. It also has a constant, that's it, right? It doesn't have any slope. It only has the constant right there. It's always a horizontal line. Okay? Give you guys a quick second to jot those down. Remember there's sketches. All right, so our language objective today is it is a blank function because. I want you to explain to me why it is the function you're telling me it is. And our learning objective is that you're going to identify graphs as different types of functions. All right, so go ahead and jot each one of these down. We're going to so the last couple slides we had a graph that we were identifying. Now we're going to identify each of these with an algebraic equation. Recording. Okay, this time I'm going to remember to change my colors on this. Okay, so what does a constant function look like? Y equals, ooh, look I left it and I need to change my, give me 1 second. It's a little bit too thin. All right, got better? Still too thin. It's awkward to write. I'm sorry. I'm not being, I know normally it's just because I'm being my usual self, but it's awkward to write with when it's that thin. Much better. Y equals A. Anything. Right? Be 1, 2, 3, 4, a million. Y equals a million. And it's always a horizontal line. Direct variation, what does that look like? Y equals, think of variables. Kx. Good job, Sam. Y equals Kx. Could be Mx. Means the same thing, right? But since we're using, that would be your constant of variation, we use the letter K. Direct variation always passes through the origin. What about identity? Y equals X, right? Just Y equals X. And I would call that our most basic parent graph. Square root function, Y equals square root of X, or Y equals X to the 1/2. Those are the same thing. What's specific to square root graphs? What do we worry about? Okay, what makes imaginary numbers? Okay, so there's a restriction on what? What do we call that? Let's use proper vocabulary. Restriction on the domain. Right? We're concerned with what's happening with X underneath that square root sign. Correct? I can use the same colors, right? Greatest integer function, what's that look like? Y equals? It doesn't have to be double though, it can just, as long as it's evident that it's a bracket. How can we explain the greatest integer function? Yep, looks like steps. Absolute value function. Y equals X with absolute value signs around it. How would we describe that? Or it looks like a V. I like how specific he is. V shape. Quadratic, and I mean specific. Y equals what? Not just X squared. What is it? No, that would be linear. No. B squared minus 4AC is the discriminant. AX squared plus BX plus C. What about in vertex form? Because they're both quadratics, right? What would vertex form look like? It still has an A, but in parentheses it's now you're right, there's an H and a K in there, remember? Everybody's just guessing whatever they can. X minus H squared plus K. Right? We're going to practice that a little bit. A rational function. What does a rational function look like? Y equals That was earlier this week. P of x over Q of x. And let's make this one red again. Nope, I need a different color, don't I? Purple. Inverse variation. It is a rational function. It's just, right, because it's a rational number, but it's specific. Y equals A over X. Where the asymptotes are always x equals 0 and y equals 0. Always. So if it's 1 over x, it would be just normal, right? But if it was 2 over x, that would mean it would be wider, but it would still have asymptotes that were at x equals 0, y equals 0. That inverse variation function always looks like that. It's like the parent graph. Okay, questions on any of these? Jacob. Rational would be something more like, if this is, you know, your xy axis, then it's like, you know, it can do that. It's shifted. You know what I mean? The difference between the two? An inverse function is a rational function, but a rational function doesn't necessarily need to be a inverse. Kind of works like that. Okay. All right, pencils down. I'm going to go ahead and graph this greatest integer function for you so you can remember about that. So my first step is to ask myself what is the behavior, what type of graph it is, and I've already said it. This is a greatest integer function. What's the behavior of a greatest integer function? I'm going to remind myself that it looks kind of like steps. And then finally, the behavior of this particular greatest integer function is translated to the what? Think about it. Think about the most basic form of this. Just like your vertex form is a times x minus h plus k. It's always the difference between x and a different number. So which way is it going to go? To the right or to the left? To the right. Correct? Because if you take that out of there and say that x minus 1 equal to 0, what happens? It becomes 1. If you ever forget, just think about that right there. If you look at that and set it to 0, it's going to be x equals 1. So if it was x plus 1, which direction would it go? To the left. Okay? So this one's going to go to the right. I'm going to double check that right now. All right, so what do you think I'm going to start with? No. 1. All right, I'm going to check it. So if I put 1 into this greatest integer function, I get 1 minus 1, which is 0, which is 0. Remember, whatever comes out of there has to be an integer. If it's inside of it, it can be a decimal or a fraction, but once it comes out, it's got to be an integer. Is it an integer up above or down below? Remember that? Some of the looks on your faces, you don't. Okay, so let's keep talking. So 1, 0, that is in fact a point on my graph. So let's put in 2. 2 minus 1 is 1, which is 1. So I go over 2, I go up 1. The next thing I need to check is there anything going on between 1 and 2? What's going on between 1 and 2? So I'm going to put in 1.5. If I put in 1.5, I get 1.5 minus 1, which is 0.5. Now, with a step function, if I put in 1.5 and I go up to 0.5, am I allowed to be in the middle there on a step function? No, so it falls down because it didn't quite reach the next step, it falls down to here. So your answer is still 0. It didn't get quite up to 1. Remember that? A little bit? Right? It didn't get quite up to 1, so it's just the answer 0. Let's try 2.5. What happens with 2.5? 2.5 minus 1 is 1.5. Did 1 point, so I go over to 2.5 and I go up to 1.5. Did 1.5 make it? So it falls down to 1. So that's why this goes continuously and then stops with an open circle here, and continuously and stops the open circle, and continuously just like this. You only have to do a couple of them to see the behavior of it, and then you just keep going because it'll be constant that way. Got it? We'll do more of those tomorrow. I'm going to do at least one more where you've got something like this, and see what that does to the graph. All right, for a little bit of review. Okay, so I'm going to go back and look at my steps. My steps are identify the type. This was a greatest integer function. Identify the behavior. I said it looks like a step, and then it's going to be translated to the right. Draw my table and graph it. Go ahead and copy that down. Okay, let's try another one. Can somebody identify what type of function this is? Rational. This is a rational function. I'm going to go a little bit quicker through this one because we just did these. I'm going to identify the behavior. First of all, what does a rational function look like? Looks like this. Okay, it looks like an identity function, not an identity function, but an inverse function. And what do I know specifically about rational functions? They have what? Asymptotes. Where's the asymptote of this rational function? X equals -1. X can't equal -1, therefore my asymptote is at -1. Correct? All right, so now I know the behavior because the behavior works around that asymptote. So where would you start? Where would you guys start? I would start at 0. So I would have -1 times 0 plus 1 equals, what's -1 over 1? -1. 0 and -1. Can't really go in this direction, right? Or this way. Going like this. It's either going down this way or up this way. But I really don't need to put that in my table because I know it's going one way or the other. Let's see which way it's going depending on what I get when I plug in number 1. So let's substitute in 1. What do I get when I substitute in 1? What's 1 over 1 plus 1? -1/2. So as I go over to 1, it becomes -1/2. I wonder what happens when I go to 2. What does that become? -1 over 3. So what do you see happening? It's gradually going in this direction, right? So this rational function must go like that. Now let's see what the behavior is on the other side. Let's predict. Which quadrant do you think it's going to be? You guys remember your quadrants? This is the first quadrant. This is the second, third, forth, I'm guessing it's going to be in your second quadrant. Okay, so what do you want to plug in? -2. If I put in -2, what do I get? It's just 1. -2, 1. Don't need to go in between -1 and -2 because this is either going to go this way or this way, right? Okay, so now what? -3. What do I get if I put in -3? ½ I'm guessing that I'm going to get the same values, only they're going to be positive instead of negative, right? Isn't that the way it's going? So -3, I get ½ So if I put in -4, what do you think I'm going to get? 1/3, and so on and so forth. This is going like this, just like we thought. We've got 7 minutes. So you guys jot that down as quickly as you can so we can do the last one. Okay, so second to last one. This is a absolute value. You guys are really comfortable with this one, right? Sure we are, Mrs. Mahler. Absolute value function. I'm going to ask myself, it looks like a V, and it's translated to the left, right? This is +2, so that really means y equals the absolute value of x minus -2. Think of the behavior of the graph. What's going on? So that means it must be shifted this way. But I'm going to double check with my table now. So I'm going to start with -2, and I'm going to get -2 plus 2 is 0, which is 0. Perfect. What would you substitute in next? -3 or -1? Let's do -1. If I put in -1, I get -1 plus 2 equals absolute value of 1, which is 1. So -1, 1. I really only need one other point. Correct? Nope, not 0. Why do I need -3? To prove not just the V-shape, but the, what's that word? Opposite value functions are always symmetry. I got to prove the symmetry. You're right, it said it makes a V-shape, but I want to get that vocabulary in, the symmetry of it. Okay, so when I go over to -3, I get absolute value of -3 plus 2 equals the absolute value of -1, which is 1. You don't need 5 points, right, Sam? As long as you understand what the graph is doing, right? There's your absolute value function. Questions? Okay, copy that down. Something for us to talk about. Let's talk about match each graph with equation at the right. So number 4 is what type of function? A rational function. Which one of these equations matches this graph? C. Number 5, guys, please don't pack up. Number 5, which one of these equations matches that one? B. Good. We will talk about the other ones tomorrow, but let's do our closing thought. What did you learn today? Freeze. Different functions. Hold on. What is the difference between a rational function and an inverse function? No. Inverse function and rational functions. Inverse function is a rational function, but what makes it an inverse function specifically? The translation doesn't translate, so the asymptotes are x equals 0, y equals 0. Okay, we'll go over this tomorrow. Have a great day, guys.